Hey everyone, Amadeus here from Cognito. So what I want to do in this video is give you a walkthrough our longitudinal and transverse waves lesson from our new learning platform. So I'm not going to kind of explain to you all the details from this subtopic. I'm going to instead go through the questions that we have in this lesson and sort of explain as we go and show you how I would approach the questions. So as you can see here, this lesson talks about the basics of waves, and then the equations to find frequency and to find the wave speed. And then finally the difference between transverse and longitudinal waves, which is really important. So like most of our lessons, it starts off with a video, which you may well want to watch before watching this video that I'm doing now. And then we get a whole bunch of questions. So first up, it reminds us that waves transfer energy from one place to another without transferring matter. And what that's saying is that, say when light from a light bulb comes and hits your eye, it's not transferring any matter, any like mass from the light bulb to your eye, only energy is being transferred. And that's a really important thing about waves. Okay, next up we've got a question. So this says the wavelength of a wave is the something of one entire oscillation of that wave. And remember, an oscillation is like one entire kind of wave as such, like one up and down. So here that would be going from here all the way up, all the way back down, and back to the middle again. And so this answer here is distance. Yeah, the wavelength is the distance of one entire oscillation. So we can put distance. Okay, next question. The amplitude of a wave is the maximum something from the equilibrium position. Yeah, so from the x-axis. And for this one, you might think distance as well. But actually we use a special term called displacement here. So it's kind of how much it deviates from the center. So the amplitude basically is from the x-axis to the very top or the very bottom. A common point of confusion is to think it's from the very top all the way to the very bottom, which is not. That would actually be two amplitudes. Okay, next we have the something is the time it takes for one entire oscillation of a wave. So this is like wavelength, but rather than talking about distance, it's talking about time now. So the time it takes for one entire wave is the time period. Oops, spelled that wrong. Yeah, time period. All right, next up, the formula for frequency. So there's actually a couple of ways to find frequency, but the way they're talking about here would be this middle one, where frequency is 1 over the time period. Remember, frequency tells you how many oscillations there are each second, whereas the time period tells you how long each of those oscillations is. All right. And the unit for frequency, not meters per second, that's for speed. HS isn't really on this course, but hertz. Yeah, so Hz is hertz. So if the frequency is 50 hertz, that means that there are 50 oscillations each second. Okay. So here we've got a question. It says a wave has a time period of 0.2 seconds. What is the wave's frequency? So you may know how to do this already, but I want to show you this hint function that we have. So these hints are on a fair few questions, mostly on the calculation ones, and they help you kind of go through it step by step. So if you look first, it says use the formula that links the frequency and the time period of a wave, and then plug in the values from the question to calculate the answer. So that's like one overview in case you aren't quite sure what to do. But if we try again, the first thing we want to do is write down the formula. Remember, that's the formula that we saw up here. So that's 1 over the time period. Once you've written down the formula, you want to write down all the important figures from the question and then plug them in. So in this case, the frequency is going to be 1 over that time period of 0.2 seconds. So we just put that in the calculator, and that will be 5 hertz. And that's our answer. So remember, this is the technique that you want to use for any sort of calculation question. Write down the formula, plug in the values, and you get your answer. Okay. So the formula for wave speed this time is this top one. So wave speed is equal to the frequency of the wave, so how many hertz it is, times the wavelength, so how long each wave is. You're basically doing how many waves there are each second times by how big each of those waves are, and that will tell you how far it's going each second. Alright, so here it says a wave has a wavelength of 3 meters and a frequency of 20 hertz. What is the wave's speed? So again, you may know how to do this straight away, but if we go through the hints, we get the overview of what to do. Then it tells us to write down our formula. So wave speed is frequency times wavelength. Then it says write down all the variables. So because there's a few different numbers involved, it's sometimes helpful to write down what each thing is. So here, the speed is what we don't know. The frequency is 20 hertz, we're told that up here. And the wavelength is 3 meters. So then we can plug these into our formula that we've written. And that will tell us that speed is 20 times 3. And if you put that in your calculator, that will be 60 meters per second. Oops, didn't mean to press that there. And that's it. Does that make sense? So the idea with these hints is that if you kind of get into the pattern of doing these steps, then all the calculations will be fairly easy. Sometimes they're a bit hard if you have to rearrange and stuff, but they all follow a pretty similar sequence. All right, almost at the end now. So a wave where the oscillations are perpendicular to the direction of energy transfer is a transverse or longitudinal wave. So this is basically saying if the wave is traveling from over here to here, yeah, wave's going this way, and the oscillations are perpendicular to that, so up and down, so it's kind of oscillating like this, what type of wave is that? And that would be a transverse wave. Yeah, transverse waves, like the electromagnetic spectrum, like light and infrared and stuff, they all oscillate perpendicular to the direction that the wave is traveling in. Whereas if the oscillations are parallel to the direction of energy transfer, and remember, energy transfer here basically just means the direction it's traveling in. They're both the same, really. Then that would be longitudinal. So this is like sound waves rather than electromagnetic waves. And that's it. So we can see it tells us our score, and that's basically the lesson over. So I hope that all made sense. Let us know what you think of these in the comments, because we can do more videos like this. But anyway, I hope you found that useful. I'll put the link to this lesson and our platform more generally in the description and as a pinned comment, so check that out. And I'll catch you next time. Thanks.